Greetings. Welcome back to our lecture series on Morse theory with no background. This is our lecture 6, and as we can see, this title is quite long, but don't get intimidated. Um, we're gonna make it light and breezy today, try not to cover too much stuff. So basically, as the title suggested, we're going to cover basically two things. The first one is a finite number of critical points for a very short lemma, and we're gonna use a very interesting proof technique to prove this particular lemma. And we're going to cover the some introduction to something very important in differential topology slash I guess just topology in general, which is called handle decomposition. It's used a lot in Morse theory and also in a lot of I, s- well, I guess like not only in math, right? Like handle decomposition, you can think of it as like playing Play-Doh, something like that. Which is kind of fun, right? Like everybody has played Play-Doh when you're like very little. Anyways, let's not get too far off the topic. Well, first, let's do a quick recap. What did we cover last time? So we finally finished the proof on our theorem about our domain space being diffeomorphic to S2, which is our little sphere looking thing, right? So let's state the theorem real quick. So let M be a closed surface, which also implies it's compact. And suppose that there exists a Morse function f that maps from this space to some real number with exactly two non-degenerate critical points and no other critical points in between. So, yeah, no other critical points on the surface. Then M is diffeomorphic to the sphere S2. And keep in mind, S2 lives in R3, so it's an embedded manifold that is basically the surface of a three-dimensional sphere, right? It's called S2 because it's on the surface. And okay, so basically, our very very long proof basically boils down to this little picture I drew at the very end of the last lecture. If you are interested in looking at the entire thing, feel free to go back to the previous lectures and refer to these proofs. But here, basically, what we are trying to do is we kind of like cut off our top, our critical point, P naught, when we cut off this little top part, and this forms a local space that looks like a dome, like an upside down bow, right? And then we also do the same thing with, just to, I guess, clarify this, let me circle this. Yeah, this is the dome I'm talking about. And we also have this little bottom space that's also like a bow-shaped place that also includes our minimum, which is Q naught, right? Okay, so these two spaces, we cut those off, and then we also have our middle space, which looks like this, ugly looking thing that's kind of like a cylinder, but it's like, it can take any shape because functions can be weird. And yeah, basically we have those spaces, and by the way, those are like locally because like on the we can use coordinate transform to make our minimum and maximum, our those two critical points, to look topologically indistinguishable from those two bowl-looking things slash dome-looking things. And then basically the top one is the top dome. The dome will be diffeomorphic to our D2, the disk that live in the two-dimensional space. And the bottom one, if we attach the bottom one with our cylinder-looking thing, which is this little thing we can look at. So when we glue those things together, we actually used a lemma that's not covered yet, and I will actually state it in this lecture for completeness. And yeah, this glue lemma basically tells us, oh, if we glue this ugly looking middle part to the bottom bow shape, we can actually form a entirety, this whole space to be also diffeomorphic to a another disk, which is another D2. So once we do that, we can glue those two things back together. Basically, like if we look at those two red parts on the two disks, we can glue those two boundaries and then form a sphere by gluing the boundary, right? Yeah, so this is basically the gist. Of course, I'm like just like hand waving this entire proof. The proof itself is very rigorous, and I've skipped a lot of details, trying to just give you guys some intuition. And also, yeah, the detail can be very tedious. It is very, very important to know about this if you want to learn, this subject matter. But here, again, this is a class called a lecture series called Morse Theory with no background. So I'm not expecting everyone to be on that mathematician level. And to be honest, I am not at that level yet. And here I'm just trying to introduce you to those concepts. And okay, so let's actually jump into today's material as we just talked about this very grand theorem, that very nice property that we have for our space, our compact manifold, arbitrary compact manifold, to be diffeomorphic to a very structural, very nice looking structure called a sphere S2, right? So like what else do we want to cover this time to like kind of tie everything together, right? So first, let's state something that we forgot to state in the last lecture, which is a lemma that we used for gluing those two parts. So let's state it right here. Lemma. Oops, that's a pencil, not a pen. Oh, that's the wrong color. Sorry about that. There we go. Lemma, let K be a map from the boundary of D0 to the boundary of D1. So, for instance, if we look at this, right? So if we say this is D0, this is D1, the boundary is the red part, the boundary is the red part, and we have a map that maps from this red part, right, to this red part. That's our map K. Does that make sense? Great. Okay, so this is our map. And let this map be a diffeomorphism between the respective, I can't spell, respective boundaries of the two disks D0 and D1. Then we can extend K to a diffeomorphism. So we can actually make our entire disk. Well, this is a trivial example, right? It's because like we have a map that maps from this to that, the boundaries, right? To each other, then like the entirety of the space maps to the other space and they're the same space. So this is kind of a trivial example. Um, Let me finish this real quick. Yeah, of the disks. But they can also like take arbitrary like radii, right? But yeah, that's also kind of a trivial case. But then like what's really important about this is that we can, if we have some diffeomorphism that can map between the boundaries of two disks or slash two sets to geometries, then we can extend this to the entire set. That's the takeaway, basically. So those boundaries are basically closed sets, right? Like this basically implies the entirety, which is pretty interesting to think about. It's kind of like a, it's I would say it's a little bit related to the gluing lemma. It's not that much related, actually. And yeah, I also realized I haven't touched on this, but this is actually used in the last proof that we talked about in the last lecture. Here is just listed for, um, I guess, completeness. But yeah, that's a very interesting lemma that's used in the proof, which is important. It is, I think, is somewhat related to that gluing part because you are trying to like match the parts that you are, which is the boundaries that you are trying to like glue together. Well, anyways, here is the important lemma that we are trying to prove today. Let's just do one lemma at a time. So today we're just gonna focus on this lemma, and then we're gonna kind of talk about a little bit of handle decomposition, and we can call it for a day. And let's state the lemma. So the lemma is this: a Morse function, and Morse should be capitalized. Sorry about that. We need to put respect to Mr. Morse name. So a Morse function f that maps from a manifold to some real number, again, similar setup, defined on a closed surface. Again, a closed surface, a compact manifold, standard setup, which, as you can see, we're building up on the last theorem, sort of. So this is sort of an extension, I guess. Has only a finite number. So in the last case, we said we have two critical points, right? But here we're saying, oh, this function can be anything, right? If it has two, it's M is diffeomorphic to S2, to the sphere. But if it has more, it still has to be finite. It just can't be an infinite number of critical points. Why is that? We're going to prove it today. And the proof will be, well, if you look at this thing, right? What are we trying to prove? We are trying to prove there exists only a finite number. This kind of screams out something to me personally. Kind of, you want to use something called a contradiction to prove this. So today we're actually going to also cover a little bit about contradiction. So what is contradiction? I think it came from a Greek word, a Latin word, yeah, Latin word called I think it's contract. Well, I am gonna butcher it. It's something absurdum. Basically, it's like trying to say something that's so absurd, no pun intended, such that this is just never true. So the converse of it is always true. Okay? So I'm also, this is not the official definition of this, but I sort of just remember it as such. But contradiction is basically just you try to like propose something that's so absurd, and you prove that this is never true. So the converse of it is always true. Okay, so how do we start? Right? We always want to propose something. So we want to assume something to be true first, and then we want to say this is never true, right? So let's do this. Let's start by assuming f on a closed surface, right? This is just the condition that we're given, has an infinitely many, infinitely many critical points. And let's actually underline this real quick. So this is what we're trying to disprove. So we're going to propose this to be true first. Now we have something to work with, right? So now we actually gain some information. We're kind of assuming this to be true, so we can use this assumption to keep proving. And then we find something that contradicts our original statement. After we use these conditions, then we reach, our final conclusion that we have a contradiction. So let's start. First, we know M is a closed surface, so M is compact. We've proved this already. So this implies that there exists a convergence subsequent of this sequence that we propose. So P1, P2, P3. What are those points? Those points are our critical points. Okay, so what is a convergent subsequence and what is a sequence? So a sequence can be any arbitrary collection of points, right? So this is just a sort of a hand-wavy definition, but any number of points that goes to infinity, which is of infinite many critical points. So this is a sequence, just some arbitrary numbers, right? And if we have a compact set, by a theorem called a Bolzano-Weierstrass theorem, and I don't know how to spell this correctly, so I'm gonna write BW theorem. You can search that up. Very important theorem in real analysis. So by this BW theorem, Bolzano-Weierstrass, I am gonna try to spell it for you just so you can. Bolzano-Weierstrass. I'm pretty sure it's not spelled as that, but good luck. Anyways, yeah, this is Bolzano-Weierstrass theorem. Basically states if you have a not necessarily compact but closed and bound. Well, if you have a bounded sequence, a convergent sequence. Uh, every convergent sequence has a subsequence that's also convergent. Basically, and yes, and this compact set bounded and closed and bounded set basically ensures that our sequence is well behaved. So it is a convergent sequence. So if we have a sequence that's convergent, then there definitely exists a convergent subsequence of this sequence. Whew, that was a mouthful. Okay, great. Now let's proceed. So what? Let's kind of denote this convergent subsequence. So let's denote this as Pn1, Pn2, oops, Pn2, da 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 of the sequence. So this is the convergent subsequence. Okay, great. And then let Pn be its limit point. Limit point is also a very important concept. So here, Pn is just this P1, P2, P3, da da da. All those points will converge to that one point. And P naught is that point that it converges to. So you see a lot of people writing like limit of some sequence, let's say like, or limit of some function, right? F of x, x of n, let's say, or limit of xn, or something like limit of some sequence, let's say Sn, and when n goes to infinity, right? This goes to equals to something, right? So if this is Pn, then Pn is the limit point. This is the point it's converging to. So Sn is converging to P naught or slash. This is converging to P naught. Xn is converging to P naught, right? So this is the point that your sequence is converging to. Okay, great. Let me erase all that. And I accidentally erased that. Okay, yeah, so let P naught be its limit point. So basically, let's denote our sequence as such. So this is our subsequence, yes. So this subsequence converges to Pn as well. So basically, if you have a sequence that converges to something, then in a complete metric, you also have your subsequence converging to that too. And I don't think you need a complete metric for that, actually. I can double check on that, but yeah, not that important for right now. Anyways, Pn, our subsequence Pn of I is contained in the neighborhood U of P naught. That's understandable, right? So there's definitely a neighborhood that contains this subsequence. that also contains the limit point. So using local coordinate system, let's use the small x and small y. So our partial at P in the first argument, when we take the derivative, and the second argument, when we take the derivative, depends smoothly, oops, on P, right? Because we are on a smooth manifold, so yep. Okay. Then these two values take value 0 on the sequence Pn1, Pn2, da 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 of critical points, right? Because that's the definition of what a critical point is, right? All the partial derivative, first order partial derivatives in all the arguments in its local coordinate chart is 0. Okay. And these derivatives also take 0 at P naught, right? Because that's the limit point. And since P naught is the limit point of our Pn1, Pn2, our subsequence, thus P naught is a critical point, right? That makes sense. Also, it satisfies the definition. So of the function f. What does that mean? That means all critical points are non-degenerate and isolated. Well, it doesn't mean that. It's just we're restating, right? What a Morse function implies for our critical points. That's not what the previous meant. This is just something that we already know because we have more a Morse function. But then our subsequence here, this thing converges to P naught, right? As we just said, P naught is our limit point, and we have this convergence to from this subsequence to the limit point, which will form which forms a contradiction, right? But why is that a contradiction? We just said that there exists a neighborhood, right? Right here. So this set is contained in some neighborhood of P naught, correct? So let's draw this little neighborhood in red. So we have this neighborhood, right? And this is our P naught. Basically, in this little neighborhood, we have a infinitely many critical points. And we don't like that. We want everything to be isolated. We want actual isolation on in terms of the critical points. But if we actually have a infinitely many critical points, then we cannot obtain such isolation. because of this. This is basically the meat of this proof. So if we have a limit point and we have a subsequence that converges to such limit point, then this subsequence is contained in some neighborhood. And we cannot have a isolation of critical points. So that concludes our proof. Great. Okay, so this kind of finishes our little section 1.4. And we're going to cover a little bit about our next section called handle decomposition. As I said in the beginning, this is kind of like Play-Doh. You decompose well, structures and then glue things together slash stitch things together and then add, interesting shapes to like kind of construct a manifold. And this is a very important study in the study of differential topology. And let's jump in and define a few things, and then we can end this lecture. So I start by doing this. Let's consider a Morse function. And again, we're going to state the classic example of going to, this is a classic setup defined on a closed surface again. Standard setup, very classic. And assume that M is connected. What does connected mean? So don't worry about this for now. So this also means M is arcwise connected. So in other words, we can say that any 2 points P and Q on M are joined by an arc drawn on M. So if you just draw 2 points on the manifold, they can be connected with a an arc, right? So like this is a little bit similar to what a convex set slash non-convex set is, except well, this is basically a non-convex set, right? So this is like for a straight line, you like kind of go outside, but then like you can draw an arc. In this case, you can kind of draw this, and then you're still fine. So this is still a closed surface that's connected. Don't have a really good example currently, but also don't worry about this for now. This is just a definition, and we will talk about this a little bit later. Okay, and let's move on. And our function here, and we denote M plus the subsurface of M consisting of all points at which f takes values less than or equal to the real number. So, I guess this is not a plus, this is a t. Sorry, though, my bad. So yeah, my handwriting is tedious sometimes, so that's my mistake. So this subsurface is defined for all the points on M such that f of p is smaller or equal to the value t. Okay. Next, we denote LT as the set of points where the value of f is exactly t. And we call this LT the level curve, or we say the level set at F equals to T. So the subsurface empty is everything below the surface curve LT. And the level curve LT is the boundary of the subsurface empty. Right? That makes sense? And next, oops, the function f that maps from M to R takes the maximum M and A and minimum small a. So we have a capitalized A and lowercase a. And we have our empty equals to the empty set for t smaller than a. And empty equals to M for t greater or equal to big A. Right? So if you have a set, let's just draw a sphere real quick because I love spheres. Right? So if you are looking at something that's below this part when we take t, right? So we have an empty set because there's nothing that we're including. And if we're looking over here, this is our, let's say T1, this is T2. If we're looking at something below this, if we take a slice here, what do we have? We have something that looks like a dome, right? Like a bow, correct? Yeah, that's what we get. And also keep in mind what we get is like the surface of it. So only this part. And yeah, only on the surface of this bow, right? Okay. And if we go all the way to the top and then basically look this way, we get the entire sphere again, right? So in a way, you can also think of this as like basically putting this whole object slash well in this case a sphere into a basket of water, like just immerse it into the water, right? And then see how much is underneath the water slash like looking at an object in a way such that you are slowly like immerging this object like sinking it under the water slowly, so basically all of your topology will slowly just get under the water, and the underwater part is the focus of study, right? So this is like why we're going to define this thing so that we can like have a transition of like looking at different level sets and different subsurfaces so that we can study it better and then study how those critical points kind of impact how our topology looks slash how our functions behave on certain topology, right? All right, let's erase this drawing real quick and let's see. Um, okay, so I think that's yeah. Let me maybe draw two more remarks and then we can call it. So here first, MT will start from, so starts from the empty set and changes into M, right? So you can think of it, this function, as a height function. And we can think of this as sinking M gradually, right? As what I just said, in the water level. And MT is the portion of the surface underwater, right? when the water level is T. Okay, great. So that concludes our lecture for today. And next time we're going to cover critical values again. And we're going to prove another lemma about diffeomorphism. And we're going to talk about what happens in between two critical points, slash in between two critical values. And yeah, we're going to prove this I guess a theorem, yeah. And this theorem is going to be a little bit long, but not quite as long as the previous one. And there will be more pictures on this proof, I think. And this proof will probably take two lectures instead of three, because I think the last long theorem took three lectures. And I don't know, long proofs are not really my thing. I mean, they are kind of like they give you a sense of accomplishment, but sometimes you're like, oh my gosh, this is long. How do I follow this? Well, this is also sort of my job to make it more fun to you, to be more digestible, and also like, yeah, feel free to give me your input slash your feedback, and I would really appreciate that if I can, learn from you and help you to learn as well. So, win-win, right? Anyways, that wraps up the lecture for today, and thank you so much, and I will see you next time.